Hi everyone, we are going to see a topic called multitask learning in our deep learning course. So before we go into this topic, there is a small bite-sized learning for you. So which goes like this. The first automated driverless car was developed in the year 1977 by Shubuka Mechanical Engineering Labs in Japan. This car was capable of identifying painted white lines on the road and can cruise automatically at a speed of about 20 miles per hour. So we can, from this passage, we can see how old and the intuition of automated driving cars uh, started from. It was in 1977. So at the end of this lecture, you should be able to answer these questions. So pay attention to these questions. And now we go straight into the topic. So like I said earlier, the topic is multitask learning. So typically in deep learning, we develop a model for each task. So which is one task, one model. But there is another learning paradigm, which is called multitask learning paradigm. It goes like this. It's a machine learning paradigm where a single model is trained to solve multiple related tasks simultaneously rather than building and training separate models for each. So the point to note here is the tasks should be as closely related as possible for them to be combined into one unified model, which we call multitask learning model. So let's see some examples of multitask learning. So example one is a well-known example, automated cars. So imagine an automated car being driven on the road. Actually, it is not driven, running on a road. So there is an inbuilt computer or multiple computers within that car. They are using computer vision extensively. So as the car navigates every second or every millisecond, they get the picture of the road from all the directions. So using those pictures, multiple pictures, the deep learning models inside the car actually can detect multiple tasks. One of the tasks could be to detect the objects on the road. What could be the objects on the road? They could be cars, they could be pedestrians, or they could be speed bumps, okay, or what we call speed breakers in India. It could detect them. Or another task that could do is segmenting. Actually, there must be a clear division of the road from the platform or sidewalk. So unless there is a model that segments the road from the platform, there is a possibility that the car as well can ride on the run on the platform itself, which is very dangerous, right? So the segmentation is a task that does that. The third task that could happen here is identification of the depth. Depth here is defined as how far the car is from different objects on the road. So one car may be closer to the autonomous car. Another object on the road could be farther away. So when there are objects closer to the autonomous car, the car has to slow down or at times brake. So this starts the depth information, estimation of the depth can make the car decide whether to slow down or stop or run at a consistent speed. So this is we can here we have three tasks and we can as well develop three different models for these three tasks. But the MTL paradigm, that is multitask learning paradigm, helps us, enables us to develop just one model to accomplish all the three tasks at the same time. So how we do that, we are going to see that in the upcoming slides. So let me tell you the second example, biometrics. So we all know or rather familiar with how a biometric system works. Usually a biometric system is installed at the entrance of an office building. employees of the company of that office come in. They show their face to the panel that is there. There is an inbuilt camera in that panel. That camera captures the image of the face and sends that to an inbuilt computer. So here multiple tasks are possible. First task could be identify the features of the face. What could be the features of the face? Eyes, nose, ear, forehead and things like that, correct? Or hair color and things like that. So that is one task. The second task could be identifying the right emotion, whether the face is happy or face is sad or face is neutral or face is surprised and all that. So capturing the emotion could be a second task. Another task could be take the photo of the face and determine or try to determine or predict whether that face signifies face of a female or a male, or it can approximately determine the age group that face the person with that face belongs to. So like that multiple tasks are possible, but all these tasks can be done using different models. So three tasks means three models, but MTL again helps us to combine all these three into just one unified model. So this is another example. Now let's get into what are the primary purposes for which MTL came into being. So there are two purposes. One is to uh, give efficiency. So efficiency is the matter of achieving more with less. Okay. So here the efficiency we are talking about is sharing multiple layers of the network among tasks. So we have multiple tasks. Instead of if we develop multiple networks for different tasks, each of them will have their own set of parameters, which means more computations. More computations means more power consumption, and in a data center, if this program runs, there will be more cooling consumption and all that will be required, right? But by combining these three or n number of tasks, related tasks into one model, one unified model, we can share a lot of computations or parameters and hence computations, and we can reduce the computations significantly. This in turn can lead to reduction in the amount of resources consumed by this this system. So this is efficiency, right? Second purpose is to do better generalization. So let's understand generalization using an example. For this, imagine a boat that is parked in the banks of a seashore. Okay, a bank of a seashore. Okay, so usually seashore is a kind of sand, and there is a boat that is parked on the sand, and the water in the sea usually is blue background. Now let's say you have a network, you model a network, and that network is fed with so many number of this kind of images: blue background, boat, mud, bank, right? So now the network learns, by this training, learns to recognize a boat. But there is a catch. It recognizes the boat on a blue background. So which means it memorizes or rather overfits the blue background. Okay. Now you have a model in place. Now you do inferencing on this model, in which you give another image as an input. If you give an image that is boat, similar one, the network will correctly recognize that as a boat. But what if you give a cat with the same blue background? It has already memorized the blue background, right? So it will say a cat as a boat because it has learned and memorized that blue background means boat. So this is memorization or overfitting. And this is the case when just one network is developed for or built for different tasks. Now assume that we have a we have a unified model, and where we force the same model to do other tasks. The recognizing the boat is image recognition, but assuming that we train the same network to do two other tasks as well. One is, say, like we have seen earlier, segmenting water in a different color and showing mud in a different color, showing boat in a different color. This is one task. Another task could be just draw a boundary, right, around the boat. So this is another task which is object detection. So by making the network to do more tasks at the same time, the network is forced to learn the geometry of the shapes that are there. So which means it learns a generalized representation of the images that are fed to it. Now if we give inferencing on this model, it will not memorize that blue means boat. It will try to correctly identify boat as boat and cat as cat. So this is an example of generalization. So an MTL in summary is built for two purposes. One for achieving efficiency and second for doing better generalization. So this is a model diagram where, like I said earlier, there are three tasks. The first one is uh, a classification task. The same image is given. This is the image. Okay, there are three models here, right? As you can see. So this is model 1 and this is model 2. Okay, this is model 1 and this is model 2 and this is model 3. Okay, and as you can see, right, the same image is fed to all the models. Same image, right? Same scene is fed all to all the models. Okay, but the output is different. This one is doing a sort of a classification task. This is doing an object identification task. One object is identified here. You can see here, right? This one is doing segmentation task. This is shown in different color. This part is shown in different color and this is shown in different color. So mud is shown in different color and all that. So this is segmentation task. So this is the usual way of doing deep learning where there is one task, one model. So multiple tasks means multiple models. This is traditional way of uh, doing object related tasks. Instead of doing this, we can do in a different way. In this way, which is actually the multitask learning, one image, we have this image, okay, there is only one model, the whole thing is one model, okay, and what you see here is instead of having three models, we have just one model where this part is shared, okay. So each upright rectangle, right, this white color is one layer, this is another layer and so on. So some of the layers are shared uh, between between different tasks. So this is one task, this is one task, this is another task, and this is another task. So there are three tasks here, and the first part of the network is common for all the tasks together, and the second part of the network is task specific. So there are, in this particular example, there are four rectangles, that is four layers for task 1, and there are again four layers for task 2 and four layers for task 3. Okay, so let's understand this through a diagram. So this is a shared backbone, as you can see here, right, in this infographic. So the arrow here represent this one is called head. Okay, it's also called shared backbone, and there are five layers, as you can see by the upright rectangle, white rectangle. There are five layers here. So this is called backbone. The second part is called head. So there are multiple heads here. This is first head related to the task object, that is image recognition. This is second task, which is the head related to object detection. Third is the head related to the task of segmentation. Okay. So there are multiple tasks here, as you can see, and the parameters are shared here. Okay, the layers are shared here. So there are multiple ways in which the sharing can happen, right? So like I said earlier that these layers are shared. So these two layers are shared in two ways. Okay, there are two ways of doing MTL. Uh, the the MTL is done by sharing the layers. Okay, so there are two ways of doing such sharing. The first way is to have some specific number of layers, okay, in the backbone part, which is the first part, and some other specific number of heads or some other specific number of layers in the head part, okay, which are task specific. Three different heads here. So the for the heads is the size is two layers. For the backbone, you can see the size is kind of seven layers here. So you can vary this. You can vary the number of layers in the backbone as well as the number of layers in the heads. So you can have varied sizes, and this varied sizes determine where the branching should happen. So if branching can happen in this layer, right? In this layer it can happen. It can happen in this layer, or it can happen in this layer, or it can happen in this layer. It can happen anywhere. But the thing is that where it can happen is pre-decided and it is pretty hard-coded. It's already decided and it is hard-coded. Okay, that is why it is called hard parameter sharing. So this is one way of doing MTL. And there is a second way of doing MTL, which is called soft parameter sharing. In soft parameter sharing, again we have two networks. Okay, as you can see here, I will mark it here. So this is I will mark it here quickly, just bear with me. So this is one network, okay, the whole thing is one network, and this is the second network, okay. So network A and network B, okay. This network A is related to task A and network B is related to task B. Now instead of and there are multiple layers, right? And you can see here this is one layer in the network. This is one layer in the network. This is another layer in the network, and this is a third layer in the network, and this is a fourth layer and in the network, and so on. Similarly, there are networks. This is one layer in the network, second layer in the network B, third layer in the network B, fourth layer in the network B, and it goes on like that. Okay, and this is sort of two networks here, and both are variations of a type of neural network called convolutional neural network, which we will study in one of the upcoming topics. So instead of sharing the parameters the hard way, there is another network called cross stitch unit, which I will mark here. So there is something called cross stitch unit, and this cross stitch unit is this part, okay, and this cross stitch unit takes in inputs from one layer from here and also from here, and decides how much of the output from here is passed to either to this place or to this part of the network, the second network, right? So this way, and this alpha value, this is alpha is some value, it can be 0.5 or 0.2 or 0.9, it's some value, let's say from 0 to 1, okay. So this alpha takes some, let's say 50% of values from here and 50% of values from here, and blends them together and share with to this part, okay. So the point is how much of the output from this network is shared, and how much of from values from this network is shared across is determined by this alpha values that are here, and this alpha so many alphas are there which form another network, which I said earlier as cross-stitch network. So cross-stitch network dynamically determines how much of sharing should happen. There is nothing hard-coded here, and hence this name, soft parameter sharing. So this is a quick explanation about how multitask learning takes place. And multitask learning is not easier uh, to implement uh, because it is in the real world it is quite hard to determine tasks that are related to each other. Typically, this learning happens through trial and error, and a lot of training would be required. And it is up to the machine learning or deep learning practitioners' decision to determine whether to implement MTL or not, given tasks in hand. So with this, I will complete this lecture, and thank you for listening. Bye for now.